Nowadays, especially the banking system in the city, there are a lot of transactions happening through the internet and so on, and we cannot afford to have a poor power quality. So it's something very important that all the system should be on place. Now, the key question, okay, we know that there's a power quality problem which is caused by the renewable energy, but how do we improve it, or how do we eliminate the harmonics? How do we cancel the harmonics? What do we do? Now, an obvious one, which we say, preventing the harmonics happening from the first place, i.e. stop the harmonic happening, okay? So stop them completely. There are so many ways of doing that. If I'm building a new system, let's say static power converter, and converting from AC to DC, if I increase the number of pulses, if you are studying power electronics here, if you increase the number of pulses within the converter system, that can reduce the harmonics. I'm not talking about filtering here at all, just as precaution of what you need to do. Also putting some switching regulators, either at the AC side or the DC side of the power converter, that also will will eliminate the harmonics or will reduce the harmonics. Or we have multi-level inverter topologies. Multi-level inverter topologies is a new type of inverter. It has been over the last, say, 5 years, and there's a lot of technologies there, okay? They try to avoid high switching frequency so that they can reduce the switching losses. At the same time, try to achieve as much sinusoidal as we can. However, if I have an existing system, then we have to use filters there, okay? So for existing source harmonics, we can introduce either DC filters at the DC side or AC at the AC side. Or we can combine both of them, as we'll see as well. Filters, usually we use them to improve the power factor. If you are familiar with the power factor, which is the real power divided by the apparent power there, so we try to enhance the system as much as we can. Also to reduce the harmonic power losses. A lot of people think that the harmonic does not contribute to the losses. It depends. If you have, let's say, a third harmonic at the voltage, and there is no matching third harmonic for the current, there is no losses there. Because simply V times I, if one of them is zero, so the power will be zero. However, if I have a third harmonic voltage as well as a third harmonic current, then I have a third harmonic power there. So there is a lot of power losses will be present there. And there is no always match between the voltage and the current. So I might have a lot of harmonics within the voltage, but less harmonics within the current, or vice versa. Or it could be a combination of all the above systems there. Now, this is some of the configurations for filters available. Either we use them shunt configuration, put them in parallel, and they are mainly to reduce the current harmonics. Or I can put them in series, and that will improve or will reduce the voltage harmonics. Or we can have combined together. Most of the time, the shunt configuration or the parallel configuration are used separately there. However, if I'm using the series one, we use shunt with them. So there is some sort of combination between both of them. Passive filters, these are classic ones. We all knew about them. Either I have tuned filter, i.e. for each specific harmonic. Let's say I would like to cancel fifth harmonic, seventh harmonic. Then I will design my filter so that XL and XC will equal each other for this specific frequency. So I have almost zero impedance. Usually I rely on the internal resistance or the inductance of the resistor, or we can put small value of R to cancel the harmonics there. Or we can have like damped filter for all the higher order harmonics. This is a passive one. So in a typical three-phase system, I put filter for the 5th, 7th, 11th, 13th, and then high-pass filter or damped filter for all the rest of the harmonics there. Now, this passive filter has been established for so many years, and it is well-known technology. However, over the last 10, 15 years, there is a lot of problems with them. What sort of problems there? Uncharacteristic harmonics. Suddenly, if I have a third harmonic, none of these filters is tuned for the third harmonics. so it cannot be absorbed. Okay? Another one, high cost, especially the cost of the capacitors are very, very expensive. It's almost half the cost of the passive filter goes to the capacitor there. And they're also bulky, okay? So big, huge things, as big as the copper there, okay? What else? Depends on the system impedance. What does it mean? If I'm preparing a filter here, let's say for the fifth harmonic, so I would like the fifth harmonic to come from the load or from the inverter to be absorbed there. So I must make sure that the impedance for the fifth harmonic is less than the impedance of the sources of the system there. Otherwise, the fifth harmonic will just go straight there. So before I design my passive filter, I must know in advance what is the system impedance. I need to work it out. And it's not easy, by the way. It's very, very complicated issue there. Yes? Yes, by all means.
I used to work in a company.
Yeah. لا لا صح.
كمان قاعدين نتكلموا ورا. ده مش مكان للكلام. ده مجال للناس اللي جايه عايزه تسمع وتستفيد. احنا ممكن ندي دقيقه اللي شايف نفسه عايز يسمع ولا يستفيد يتفضل عشان ما يعتمدش. الكلام بتاعي واضح ولا مش واضح؟
دكتور صلاح, as a matter of fact, they are paying a lot of attention. I'm very.
يعني بعض الناس قاعده تتكلم ورا.
لا لا it's okay.
So my question is, usually you try to problem, let's say, RF power. I used to work at Intel.
Yeah.
Usually we want to problem RF power to the glass machine.
Yeah.
And we have a matching network, and this matching network was an automated, very sophisticated algorithm because the plasma impedance is varying all the time.
Yes.
So trying to double the power all the time with sophisticated algorithm to have complete matching.
Yes.
So to try doing the same thing for the harmonics so that you have adaptive system where you build a complex algorithm
Yes.
that will match.
Yes. Excellent question.
I'm not expert in
No, excellent question. That's what I will talk about it next. You just, absolutely correct. What we have, this is what we call it a passive filter, which is tuned for some specific harmonics, okay? And these are some of the disadvantages we are facing with. Now, in order to overcome this problem there, then we have an active filter. And the active filter does exactly what you are saying. So it's like a dynamic system, okay? It's, as a matter of fact, some of them, they operate on sort of predicting the harmonics, and then like proactive, try to cancel the harmonic even before they sort of occur. But yes, thank you very much. Excellent question there. So all these are disadvantages. However, they are reliable. So believe it or not, until now, you find almost 95% of the filters used in Egypt, not in Egypt, in the Middle East, in Europe, in America, they are still passive filters, okay? But this extra 5%, and this is really sort of the new research element, which is, evolving, as you mentioned, within the new system. This is the normal single-tune filter. We're all familiar, perhaps. Just make sure that XL and the XC, they equal each other for a specific frequency. So you have very low impedance, and then you can play with the band pass of the filter, make it tuned or less tuned. There are sort of so many characteristics there. And this is the damage shunt filters for all the high-order harmonics in order to eliminate them or to cancel them. Now, that introduces us to the active filters. An active filter is a new technology, okay? We don't teach it in the undergraduate courses. We teach it for the postgraduates because it is new research area. In the Far East, especially in Japan, they are using the active filters a lot, okay? In Europe, in USA, they still have some sort of reservation of using the active filters. The reason for that, because, for any low electronic or digital system, you can try new technology. But when you come to power system, you have to be very careful. People, they don't try new technology straight away. They have to wait, make sure that everything well established, and then they try, okay? So there's always this conservative approach there. Now, classic filters, either classic configuration of active filters, either we have large offenders, for example, let's say an arc furnace or induction heating, huge establishment, which generates a lot of harmonics. So I can identify, say, this factory is generating a lot of harmonics, so let's install an active filter there. Or we can have active filter for retrofit applications. What does it mean? It means you have an inverter there coming, converting the solar panel to the grid, another one here, another one there, and they are distributed. They are not sort of combined together. And each one of them contribute to some sort of harmonics. Now, the collection of all these harmonics together at a specific point, which we can call it the point of common coupling, I can install an active filter there. So this active filter is not targeting a specific source, but collection of sources, and then at the point, then we try to catch them. So that's the whole idea of the active filter for retrofit application. In 1969, that was the beginning of the research of the active filter. Somebody might say that's long time ago. It was. Remember, when we do research, the research can take a small place, and then 20 years or 30 years or 40 years later on, start to become sort of mature and so on. Now, this one, the three authors there, established this idea in 1969. It has never been implemented. However, it did sort of make the people think more and more about the active filters, okay? As a matter of fact, this one, they tried to inject a third harmonic and use the windings of the transformer in order to cancel the multiple of the third harmonic, third, fifth, seventh, and so on. But it did not materialize. There are so many different types of active filters nowadays. Active filter based on voltage fed inverter. That's very interesting. Remember, inverter converts from DC to AC. So you have a solar panel there, which takes this DC source and converts it into AC. However, this inverter generates harmonics. Now what I'm doing, I'm using another inverter, but the other inverter I'm using it as an active filter now, in order to compensate or to correct the distortion created by the first inverter. So in another way, we try to solve the mess or the problems caused by the power electronics by also power electronics, okay? So we try to clear our own mess, if you might call it that way. So based on voltage fed inverter, we have active filter based on current fed inverter. So we are using the inverter as active filter configuration, or we can use what we call it variable characteristic filters as well. This is active filter, it works that way, and that perhaps might sort of answer your question there. So this is the inverter which generates the harmonic, causing a lot of harmonics there. And these are the harmonics in the frequency domain. We have the fundamental, third, fifth, seventh, and so on. We are only interested in the fundamental. I would like to cancel all the rest of the harmonics. So what usually we do, we take a sample of the current there through a current transformer, and then we have a low-pass filter. This is very, very low power now. Talk about milliamps, okay? Low-pass filter there. So take away the fundamental components, so I have only the harmonics, and the rest of them coming from there. Subtract them from each other. Then I have all the harmonics without the fundamental. And then I have the switching power amplifier, which is mainly an inverter, okay? And this is the active filter. And then I take this one, invert them, and inject them. So as a result of that, I have all these harmonics will bang or will cancel this one, or this one will cancel this one, and then I will end up with the fundamental component. Now, the nice thing about this active filter, or the new one, that if suddenly I have any new type of harmonics there, automatically will be sort of looked after. So it is dynamic system, it's self-sustained system, it corrects itself by itself. The reason we are calling it active filter compared to the passive filter mainly like inductor, capacitor, so they are passive element. They are not doing anything. They are just passive element, and that's it. With active filters, we have some active components like switching, IGBTs, GTOs, MOSFETs, you know, sort of switching, operating on and off, which are the components for the inverter circuit. Now, is it available in industry nowadays? Yes, especially in the Far East. I did mention Japan. You know, they are using it for harmonic compensation, flicker compensation, voltage regulations, and they are available at high power as well. So I'm talking about 100 kVA, 10 MVA, even above 10 MVA. They are using them for the bullet train in Japan there because it generates a lot of harmonics and it does pollute the grid there. So they're using active filters. As I mentioned before, in Europe, in USA, is not that widely popular yet, but you know, hopefully it will be within the next few years. Yes, by all means.
What's inherent about when we have a renewable energy and we have the inverter from DC to AC? What's inherent in the inverter that causes the harmonics? Can't we, instead of building a circuit, attach it to the inverter itself in order to do a high harmonic elimination? That we, instead of trying to compensate for this and solve it, try to look for the cause of the problem and see if we can replace those elements by another element that will not produce the harmonic from the beginning.
Excellent.
Something instead of just building extra components, go back and look for the root of the problem and see what causes this to generate from the beginning and see if we have another solution.
Excellent, excellent, excellent. Yes, absolutely correct. What we usually do, we come within the inverter itself, okay? You're absolutely right. The inverter circuit, you remember the first slides when we have a square wave, okay?
Sorry, I was coming.
You were not coming late, don't worry. Yeah.
So I maybe
Yeah.
that I asked you the question.
Yeah.
I did not
Attend it from the beginning. No, that's fine. Yeah.
Yeah.
No.
No.
That's. I tell you what. We'll just go a few slides very briefly there. Yeah. That's an inverter circuit. An inverter mainly like a bridge, okay, a single phase inverter. And the way we generate from DC to AC, we switch these two switches on this switch, we get waveform like this one. Now this waveform, it's full of harmonics there. So this is the normal operation of the inverter, okay? But you're absolutely right. What we can do, we can play within the inverter circuit. There's something which we call it multi-level inverter, and then we can improve the performance, but we cannot eliminate the harmonics completely. This is the nature of the switching operation itself, okay? So we need to filter it out. We need to have, you know, some sort of harmonic filters as much as we can. Inverter is switches, and remember, the source is DC, and the DC is flat. So even if I create AC, it's still AC coming from a flat sort of DC is there. So it needs to be, you know, definitely we need the filters there. Even if we operate the inverter at high switching frequencies, the result of switching losses will be associated with them as well. Okay, so this is the in the industry there. Now this is some of the inverter configuration. Remember, I'm trying to inject, like somebody exactly, you know, having like a syringe and injecting the harmonics to the power system there. So what we do, we store energy within the inductor. We know that we can store energy in the inductor as a current, and then I will operate these switches in a clever way, and then release this energy in order to cancel the harmonics generated by the nonlinear load or by the inverter, okay? Of course, how do you store the energy in this inductor? Either I can charge or build energy in the inductor from the main supply, or you can have external power supply connected to it. Or I can store the energy, instead of storing energy in the inductor in terms of current, I store the energy in the capacitor in terms of voltage there, and then release this energy. However, since the energy is stored as a voltage, then I need an inductor there to convert it to current, because at the end of the day, I need to inject current harmonics. With this one, I don't need, because it is already the energy is stored as a current there, okay? Of course, when I'm drawing switches like that, this is not, these are very high switching frequency and it has a complicated control circuit associated with them. So this is some of the configuration there. And this is another, what we call it, switched capacitor technique, okay? This is a new technique which have been developed at Brunel University, and we are well known within this area of active filter and renewable energy. Again, we have a capacitors here, but these capacitors are AC capacitors, and the way we operate the switches, we release the energy from the capacitor to the main supply, okay? Either we have this configuration, or that configuration, and it is well used now within the industry, especially in France, okay? Within the UPS systems. How does it work, or does it work? This is, if you look at the square wave, this is the square wave which is full of the harmonics there, and this is a voltage waveform. The other one, I still have the voltage waveform, and this is the current which is injected. If you take this current and add it to this square wave, you will end up with a nice sine wave of the current. You'll find there are two sine waves of the current here. One of them is the reference waveform, and the other one is the actual waveform after compensation. And this is, the harmonic contents is very, very, very low. By the way, usually we target the low order harmonic, 5th, 7th, 11th, 13th. We don't really worry for the high order harmonics at all. Now, some of the challenges there, whenever you try, as a researcher, you are aware of that, you try to find solution for a problem, you find another problem there, okay? So there's always a challenge. So the challenge here, imagine we have some sort of load there. This is the previous slide, okay? Now, imagine this inverter or this nonlinear load is something like arc furnace, okay? Now, some of them, you'll find that the waveform does change from cycle to cycle, okay? So it's not constant. Of course, by the time you take sample of the current, you filter out the fundamental, you inject it, blah, blah, blah. The waveform here is a different waveform. By the way, this process takes about 2-3 cycles, okay? So after 2-3 cycles, you try to compensate for a waveform which is not there anymore. As a result of that, what will happen? You will find that the current harmonics will even be worse than before, okay? So you have to be very careful here. Either I use the active filter if I have a steady system, i.e. the nonlinear cycle is repeated every, between now and repetitive one, or if it is not repetitive, then I have to use some of this clever control, genetic algorithm or fuzzy logic, or there are so many things, okay? Now, there is wave-flat transform, which I can take a window. I don't have to wait for the complete cycle. I'll just sample it there and then try to predict by looking at the first window, very, very small window. This waveform might contain such and such harmonics. Then I will send my control signal to the active filter saying that the waveform is likely to have that sort of harmonics, and then it will act accordingly, okay? If it is not, then it will adjust itself, or, as we go all the way, okay? There are some, of course, harmonic standards there, which we have to be very careful with. This is mainly the 1982 standards. Nowadays, we have to follow them. There is the EN 5160 standard, there is 61,000 standard. All of them, different types of harmonics which we have to follow them as well. Okay. Now, another challenge, this is a big network there. We are all talking about renewable energy, smart grids, and so on. Traditional systems, by the way, have the main power generated coming from the main supply and then distributed. We call it upstream, and then we have downstream, and then the power coming simply from there all the way to the system there. Nowadays, this is not like that. We have a distributed generators. We have a smart grids. So distributed generator, we might have a wind farm there, we have a solar panel there, and so on. Now, the things becomes more complicated. Let's say if I have a short circuit somewhere here, in normal power system, if I have a short circuit here, this circuit breaker or this relay will act to prevent the current feeding this short circuit. If this one doesn't act, then this one will act. There are some sort of zones there. Now, the problem we have now, if this one does act, we have another source of energy which might feed the short circuit there. So when we are using renewable energy with active filters and so on, I have to be very careful. Something which we call it relay coordination. So we don't have upstream, downstreams anymore. We have all streams now. The energy is coming from everywhere. And this is one of the challenges we are facing within renewable energy. So renewable energy is not just, connecting into the grid and hope for the best. No, you have to, there's a challenge from the power electronics, there's a challenge from the power system, and there is a challenge everywhere, okay? So there's always challenges there we are facing with. In very brief conclusion, renewable energy power quality, they are very much related to each other. Effect of the cost of the harmonics, sometimes not cancelling the harmonics could be extremely expensive. Okay, the price of the filter is quite expensive and so on, but the effect of the harmonics is can be very expensive. The power electronics, as we mentioned, it is the source of the problem, but also it is the source of the solutions. Okay, so it is the one which generates the harmonics in the first place from the renewable and so on, the conversion process, but also the filtering process is sorted through the power electronics. We looked at the passive and active filter. We did mention about 95% of the filters nowadays in the whole world is passive, but active filters are gaining more and more popularity and so on. Availability and cost, active filters still expensive, okay? So that's why people are shying away from them. Regulation standards, nowadays people, they have to eliminate the harmonics. It's not a choice. Say 10 years ago, you don't have to. Nowadays, you cannot sell an inverter circuit unless it follows the AC standard or the IEEE standards with the harmonics. Distributed generation and protection, we did mention that we have to be careful when we are dealing with that sort of thing. Thank you very much. I have another presentation. I will open it for questions. Then I have another presentation if you would like to listen about the university which I'm coming from, just to give you an idea there. Open for any questions? After the second one, perhaps?
All right.
Yeah.
And instead of the converters and the filters, we can use a computer system to eliminate the undesired harmonics, like what we do when receiving any noise upon any data. The computer system have a limitation. I mean, if the charge is above so and so, so this is 1, and if not, it's 0. So is this possible?
Yeah, thank you very much. Thank you very much. Your colleague is asking, in a way, it's similar to the question here that why don't we make the correction within the system itself? Instead of adding filters, why don't we have the correction with it? Let's say an example, if we have a power supply for a computer, okay? Nowadays, we can have a regulator which can be connected to the input or within the power supply. And this regulator will make sure that the waveform will be sine waveform, okay? We can do that. However, these devices, they operate at very high switching frequency, okay? Now, if I'm talking about low power applications, that's fine, no problem with that. But if I'm talking about, tens, hundreds of kilowatts, even megawatts, now switching issue is very, very important here, If you go to even 10 kilohertz, 10 kilohertz device switching on and off, remember, every time you're switching on and switching off, you have the current rising and the voltage falling, or the voltage rising and the current falling. And V time, these devices are not instantaneous. It takes finite time there. So this device, there's a lot of power generated, and there's a lot of losses there. So you might find that, okay, I can have, let's say, a big inverter circuit. I can control the operation of this inverter circuit to make sure that I have a pure sine wave, then efficiency of this inverter, which is usually 95, 98%, might go to 40%. Then, so it's better to leave the inverter as it is and then try to solve the problem with the active filters. It's at the end of the day, the cost, which one will sort of reveal at the end. But good question, thank you. Yes?
Thank you for the very nice presentation.
Pleasure.
I have
Yeah.
for the open field project, should we go in the design purpose for the inverter and looking for the losses, for the main losses coming from the inverter, or we have to go for the active filter and go for the material itself for the active filter? Should working with silicon or should working with high voltage devices like gallium nitride?
Yeah. Yeah. The answer is very obvious. We fire in all directions. Yeah. There is a lot of research within the inverter circuit, especially the multi-level inverter. Okay. There's a lot of research going there. Active filter, it's always nice big research area as well. I have PhD students at the time being. Actually, he is trying to operate an active filter within, very similar to one of the questions there, which is try to, for example, if I operate the inverter at high switching frequency, so that means a lot of losses, or filter, why not try to find optimization between both of them, i.e., push the frequency to a specific point, put the filter to a specific point where I can find the optimal cost and efficiency-wise as well. So somebody might say, okay, the cost for me is not a problem there, or loss is not that issue. We try to build like optimization between both of them. But yes, we can fire in all of them.
Should we go for the high voltage device, captures materials, go faster, go through the inverter, or we should go back for the design architecture for the inverter itself?
Yeah, or both of them. Both of them. That's what I'm saying. In all of them we could do. We can go in this direction or that direction.
Currently, what is the power losses right now converting from the transformation to the power?
Okay. There are two types of losses there. We have conduction losses and we have the switching losses. Now the switching losses is very much related to the switching frequency. So the higher the switching frequency, it's almost linear relationship. So the higher switching frequency, the higher switching losses. And that's why we try to avoid operating the inverter at high frequency there. Conduction losses, that mainly depends on the power rating, how much power I'm carrying. So, if I'm carrying a huge amount of power, it's not advisable at all to operate at high switching frequency. If my power is limited somehow to let's say, perhaps less than 1 kilowatt, then okay, I can operate at high switching rate. There's no problem with that. And the conduction losses would not be that high. Yeah?
I was just talking to Dr. Salah, I think 2 days ago. I'm a mathematician. I work in process technology and so on.
Yeah.
And one time I was told by a company called Transport in Santa Barbara. They are doing a high voltage switch, but they going to use the gallium nitride and some other 3-5 silicon metal because they are very efficient, and the power losses they claim that they achieve something like 2% power losses, or around 2 to 10% power losses.
Yeah, what's the devices? What's the...
I do not remember. He was a professor in
Okay.
University of California, Santa Barbara,
Okay.
who invented the inverters.
Okay.
And material, I think they use, I don't remember if it's gallium nitride or gallium arsenide. Some new material.
Used in... What's the name of the switches which they are using? Is IGBTs?
I don't know the...
Okay. Yeah.
I was at this time, I went for this interview with them.
Yeah.
Tried to help them because the process was not sustainable, it's not
Yeah.
reproducible.
Yeah.
So they claim that they will revolutionize the high voltage power transmission
Yeah.
because it will be
technology nowadays, the people using, of course, thyristors still for high power, high current will use and so on. And then after that, we have the transistor, we have the MOSFET. Nowadays, IGBTs are very, very popular. And even the IGBTs, there are so many different classifications within them. And I'm not specific, involved in the physics of the devices. I'm mainly using the application of them. But of course, I myself, I see year after year how the development within the semiconductor devices, moved up. I remember in the early 80s when I used to use MOSFETs. They were very, very delicate devices. If you just hold them like that, you can easily blow them. Nowadays, MOSFETs are different stories. But IGBTs, they've taken over as the main power devices. Yeah. Yes, Dr. Salah. Pleasure. Not really. To be honest, the sort of the cancellation, the only challenge with this one, as I mentioned before, that because by the time you sense the waveform and then you create the anti-harmonics, it takes time. So it takes about 2-3 cycles. It depends how fast your system is. Now, if the waveform you are dealing with is repetitive waveform, keeps itself cycle after cycle, then yes, I cannot see why not. However, if the waveform, something, the electromagnetic interference, usually it varies from cycle to cycle, then there's a challenge there. So there's a lot of research need to be done, using something like the waveform of the wavelet transform to try to capture windows and then to respond accordingly to this one. But yes, it is. Into this area. Yeah. Yes. Yes. Pleasure. Yes, as a mixture, of course, but talk about the elimination side of it. That's yeah. Okay. Shall I give you a quick presentation about Brunel University? Yes.